Hello.
Okay, good morning, everybody. We're going to start soon the first session of the morning, and we have the pleasure here to have Professor Eduardo Duzzioni from the University of Federal of Santa Catarina, and which is a very nice city in Florianopolis. If you don't know it, you should go there and visit. And Professor Duzzioni has been working on quantum computing and quantum information for a long time now, and he has done his master's and his PhD at the University of Federal of São Carlos, Federal University of São Carlos, and has worked with quantum objects for quite a long time and has very nice results. So he was a faculty from the University of Uberlândia, Federal University of Uberlândia, and then afterwards he moved to the Federal University of Santa Catarina, where he has been working for quite a long time. He's can tell you better. So we will have the pleasure here to see Professor Eduardo Duzzioni talking about the CAT quantum programming platform and measurements and algorithms. So please.
Okay. Oh, sorry. Thank you, Marcos, for a very nice introduction. I'd like to thank the organizing committee, particular Professor Renato, for the invitation for this very nice conference. Okay. Today, I will talk about recent results. They are fresh results from our research group in the Federal University of Santa Catarina. Okay, just a minute. Yeah. Okay, these are the collaborators. These Leticia, Suelen, Vinicius, they are my master students. César Augusto and João Pedro, they are my PhD students. And Evandro Chagas is a collaborator in our team, but he is supervised by Professor Santiago. Okay, the summary of my talk is, first, I will talk about CAT quantum programming platform. Then I will show how to use this platform to optimize gate decomposition at the high level quantum programming. Then I will introduce classical shadows. This is a technique for measurements, and how to use that technique to quantify multipartite entanglement, and how to use this technique to improve Falcon algorithm. And finally, I will show some results about quantum machine learning, which I used for regression problem, and we use Walsh basis. And finally, I will present conclusions and perspectives. Okay, CAT quantum programming is a platform developed by Evandro Chagas. Evandro Chagas, as I mentioned before, he's a one-man group. Okay, he's a very good guy, and he's from computer science, so he's very good at coding. This programming platform has a high-level quantum programming. It's an open source project, and if you are interested in to know more, you can watch quantumcat.org. Okay, there you can find all the documentation. CAT quantum programming is a platform that now our research group are using in the background of our applications, because I am not developing the quantum platform. I am developing libraries that will be used in the CAT quantum program platform. I am working on quantum algorithms and new strategy to improve this algorithms, but at the end, you are developing libraries that will be support CAT quantum programming. Okay, CAT quantum programming has three parts: Python quantum programming, the API, the libcat, that is Rust quantum runtime library, and finally, there is a quantum simulator based on CPU. The advantage of CAT quantum programming that it combines the easy way of coding of Python with the performance and safe fate of Rust. Okay, and in the case of the simulator, we have two different types of simulation that we call dense and sparse. I will show some results of these quantum classical simulations of quantum computers. Okay, the basic idea of using CAT is, okay, you start coding in Python, and if your operation is quantum, then you use the libcat. After that, libcat communicates with your simulator or with your quantum hardware. And then after the measurements, this return to our classical computer, and we interpret the results. Otherwise, if you had classical operations, these operations go directly to the classical computer, okay? As I mentioned, it's similar to code using CAT because it's quite similar to all the commands developed for Python. This is a simple example of quantum Fourier transform. You can see here there are classical elements of Python, if, else, or, but there are quantum elements such as the quantum gates, Hadamard is here. There are also phase gates here, swap, but there are other commands such as with control and adjoint here, ADJ, that's the final step of the quantum Fourier transform. Okay, so as you can see, with few lines, it's simple to implement the quantum Fourier transform. As a benchmark, let me show you a simple example. This is a portfolio optimization problem with just 4 assets. This work was based in this paper in Portuguese, in which we use CAT, Qiskit, and MyQLM. Okay, this problem was using the quantum simulator of CAT, and it's possible to see that if you simulate this problem with CAT, you spend much less time compared to the other languages. Of course, I can guarantee that today Qiskit will return the same time because, as Alexandre mentioned yesterday, Qiskit is now in a new version. So we believe it can be better now. Okay. Okay. Now I will talk about the CAT bitwise simulator. Okay. These are some results. These comparison, they were executed using Google Colab. As I mentioned, there are two different ways of simulate quantum computing using CAT. One of them using the dense simulator, and the other one is using the sparse simulator. In the dense simulation, we use state vector multiplication of matrices. And here, the goal is to achieve a final state that is the equal superposition of all basis states for 27 qubits. In this kind of simulation, it's possible to implement that in just 36 seconds. and using the sparse simulator 88 seconds. Okay? If you now try to implement the GHZ state, use the dense simulator, you spend 28 seconds, and using the sparse simulator just half second. Notice that there is a very huge difference here, because now we are using 1,000 qubits, and here we are using 27. Okay, particularly for the GHZ state, basically you has just two states, 0, 0, 0, and 1, 1, 1. So sparse simulator, it uses just operations directly on the bits, not necessarily to build a unitary matrix that will act on the state. For that reason, this kind of states is very simple of being simulated using the sparse simulation. Okay, as another example, it was implemented to use the bitwise simulator, the sparse simulator, and it was possible implement the quantum approximate optimization algorithm with 42 qubits, and it was executing a 8 gigabits laptop of RAM. Okay, you can find this paper in this reference. And what are the next steps? Okay, CAT is a high-level quantum programming, so it's necessary to go to the hardware level, okay, achieving control pills, this kind of thing, and this is being developed right now, okay. We already built an interface for IBM Quantum, so it's possible to communicate with Qiskit. And here, I am, from now on, I will show some applications that we implement using CAT. This is an application, this is a paper in which you show how to optimize gate decomposition, particularly unitary operations act on 1 qubit, but they are controlled by n qubits. And actually, we improved some previous results by Professor Adenilton, and where you show that it's possible to implement any controlled unitary gate acting on a qubit using at most 32 NC knots and 1 clean auxiliary qubit. It was also possible to improve a previous result in which, instead of control a unitary operation acting on a qubit, if you have instead a gate in the SU2 group, we improved from 20 NC knot gates now to 16 NC knot gates. Okay, this is basically our main results in this paper. Just to show you how we implement that. For instance, take here, U is in general unitary operator act on a qubit. And these are the control qubits, the any control qubits. It's possible to decompose this unitary control gate using the strategy proposed by Professor Adenilton, in which you have now U bar here, using U bar is a unitary gate, but is a special unitary gate controlled by n qubits. And now you use an extra king qubit A just to add this phase, this extra phase. So we know that a general unitary operation can be decomposed as a special unitary operation times an extra phase. For that reason, it's a simple extension. Okay, now I move to classical shadows applications. Well, what is classical shadows? Classical shadows was developed by these guys, Huang, Kuang, and Prescue. This is a method based on quantum measurements. The idea of this method is to use, as the name says, classical shadows. I mean, classical information to obtain an approximate description of the quantum state of the system. And this technique is useful to obtain local observables, expected values of local observables, energy variance, correlation function, state fidelity, linear entropy. And now we are finding other different applications, as I will show here. The idea of classical shadows can be illustrated as in this picture. Suppose that you have a cylinder here, and you have access just to send some beams of light in this direction. If you observe the shadow in this wall, you notice that, okay, although this is a cylinder, its shadow is a square. Although it is a cylinder, its shadow is a disk. So the idea is to use these two images to build an approximate description of this object, the cylinder. Okay, you can imagine that these shadows will be our quantum measurements in a given basis. Okay. The protocol of classical shadows can be summarized as in this picture. Okay, you have a quantum system. This system is described by a quantum state, rho, and will perform unitary operations. These are random unitary operations. And then you perform measurements on the computational basis, the Z basis, okay? After that, you store the values of these measurements, zeros and ones, and you also store these unitary operations. But notice that we are right here, classical representation. In this sense, it is necessary that these unitary operation, they must be easy of store, okay? You can use a very rigid and general unitary transformation. For instance, in local operation on qubits, it's very cheap to store in a classical computer, or for instance, gates from the Clifford group, that's very easy to store in a classical computer. So this is the kind of unitary transformation that we use. And at the end, all the information can be stored in a classical computer, okay? And with this information, it will be possible to obtain quantum fidelity, two-point correlation functions, entanglement witness, Hamilton, ground state, okay. The energy of the ground state Hamiltonian, entanglement entropy, local observables, and so on. So the idea of classical shadow is, okay, first you measure, we store this classical information, and then we do our questions. Okay, that is the basic idea. So with this data, it's possible to do every kind of question we want about the quantum system. Okay, because in general, when you try to understand or get some information from quantum systems, we, in general, perform specialized measurements, specific measurements to obtain specific observables. In this case, this is not the idea. The idea, the scenario in which we are using classical shadows is, okay, you have access to a limited number of measurements. Okay, this is the real life in the lab, so there is no problem to now. But here, the technique is useful when you try to know many observables, not just 1, 2, or 3, many. I will show some examples later. Okay, let's see how the protocol works. First, we apply, okay, our state rule that we don't know. Okay, you apply random unitary rotations on this state. Then we perform measurement in the computational basis. Okay, after that, we store in a classical computer these unitary operations and the values of the result of our measurements, that is 0 or 1. Then we look for a map between our state that we don't know and the expectation of these classical results. And the idea is to invert the channel in order to obtain an approximate description of rule of the state of the system. And you do this many times, okay, in order to have an average description of the quantum state. Okay. For instance, if you consider unitaries that are composed of local rotations on qubits. Suppose that you are performing measurements in the z direction, y direction, and x direction of a qubit. As you are performing measurements in the computational base, if you act with the Hadamard gate on 0 or 1, we will obtain the eigenstates of X Pauli matrix. If you act with H Hadamard and S phase gates on 0 and 1, we obtain the eigenstates of Y matrices. And if act with identity on the computational basis, we will obtain the computational basis that they are eigenstates of the Z operator. So this means that you are performing measurements on the X, Y, and Z directions. Okay? And the authors of that paper I mentioned before, they show that, okay, if you perform these measurements and you invert that map, we achieve this state. Okay, this state rho is an approximation. This is a classical shadow of the real state. Okay? Observe that this is a non-physical state because it has negative eigenvalues. Although it is not a physical state, it is able to recover all the expected values of the quantum system. That's the interesting part. And as you can see, it is very easy to describe an approximation for the actual state of the system rho. Okay, and why this technique is important, is interesting? Because the number of measurements, okay, the number of unitary operations and the number of measurements in the computational base that you need to do to achieve the expected values of operators O1, O2 until OM, I mean, you are interested in to obtain M values of observables. It depends on the precision, epsilon, 1 over epsilon squared. This is the same as you want to measure directly the system, okay? But the basic difference is here. If you want to know M observables, the number of measurements when you use direct measurements depend exactly on the number of operators. And in this technique, it depends on the logarithm of this number of observables. So if you are interested in many observables, we can have an exponential advantage, okay? But it's necessary to pay attention to this other term that is the norm shadow, and the normal shadow of these observables, they are bound by this quantity. If you are interested in Pauli operators, the infinite norm of these Pauli operators is 1, so it's okay, no problem. But it depends on 3 to the power W here, and W is the locality of the operator. What is the locality of the operator you are interested in? Locality is, suppose that you have an operator that is the tensor product of x, y, x. So the locality is 3, okay? The number of operators you have in the tensor product. And as I show in a simple example, depend on the case, if W is a very small number, this condition will be very useful. And so it will be possible to obtain information about many observables of the system with less measurements when compared with direct measurements, okay? Let's focus now when you have Pauli observables. If you have Pauli observables, the observable will be the tensor product of Pj. Pj can be identity, sigma x, sigma I, and sigma z. And if you substitute in the expected value of this operator, you find this expression, okay? U here are the unitaries, P, okay, are these operators. It's possible to simplify the calculations here so that this classical snapshot can be written depending on the identity operator. B can be just 0 or 1. That's the result of computational based measurement. And sigma j will be sigma f x if you are unitary that you draw. If your unitary is in the x direction, I mean Hadamard gate, then this operator will be sigma x. If it is Hadamard times phase, then this operator will be sigma y, and if it's identity, your operator will be sigma z. Then if you replace in the full expression for the expectation value of the operator O, we achieve this final expression. Okay, what is important here is to pay attention that, okay, just 3 possible values are the result of this expression. If your operator that we are interested in to calculate its expected value is identity, so the value for this element inside the trace is 1. If your operator is different from the sigma j is different, okay, if your operator is in a different direction in which you apply the unitary transformation, the final result of this term inside the trace is 0. But if your operator, say sigma x, and you performed the application of a unitary operation in the x direction, so the final value can be plus or minus 3, depending on the result of the measurement in the computational basis, that can be 0 or 1. In other words, I am saying, okay, at the end, you just need to find the correspondence between directions in which your unitary is and the kind of operator you are estimating. Just that. Okay? So it's very easy for a classical computer to do. Just find the correspondence, match. Okay? And with this, you are able to construct the expected value of your operators. As a first application to understand the method, we use this method to obtain a global entanglement that is based on the calculation of purity, because we are supposing here that our global state is a pure state. And as you know, probably when your global state is pure, to detect entanglement in the system, you need just to calculate the purity of the reduced systems, okay? The subsystems of the system. In this case, this density matrix rho is the density matrix of a subsystem. A subsystem can have 1, 2, or 3, and so on qubits, okay? And if you are interested in to obtain this quantity, you can write the density matrix of the system, so that to obtain this value, you just need to evaluate the expected values of Pauli operators or tensor product of Pauli operators. Okay? Here, if the subsystem is composed by just 1 qubit, then you need just to evaluate these expected values. If your subsystem is composed by 2 qubits, okay, now you need to evaluate all the combinations. Sigma X, Sigma X, Sigma X, Sigma Y, and so on. Okay, if you have n qubits, okay, the combinations are much more complex. And the application here is to quantify genuine multipartite entanglement. We used a measure proposed by Marco César de Oliveira, that's here. This measure evaluates the average entanglement in the system because it considers all possible partitions in the system. And for that, it's necessary to calculate the linear entropy of all partitions. As an example here, as an example here, we decide, okay, we fix the total number of measurements. That's n. This total number of measurements is here in the horizontal axis. And the vertical axis, you can find this global measure of entanglement. 2, because we are consider the size of the subsystem composed by 2 qubits, while the total system is composed by 5 qubits. Okay? The exact value of this measure is the dotted line. Through direct measurements, you can see the blue discs here, okay? And the results obtained through classical shadows are those with these 3 values. This quantity R was defined using as the ratio between the number of unitary that you draw at random and the number of repetitions for each draw. As you can see here, there is no great difference between classical shadows and direct measurements. Observe that when you deal with 2 qubits, in order to obtain all the possible observables in the system, it's necessary to evaluate 15 observables. And for each observable, we established that you'd use 1,000 measurements for direct measurements, okay? For each observable. But now, if you consider the same state, the GHZ state, we observe that using classical shadows, it's possible to achieve the exact value using a less number of measurements compared with direct measurements. Okay? This result becomes more clear when you increase the size of the subsystem. Okay? So we extend this analysis considering W state. W state, okay, it seems that's not good when the size of the subsystem is 3, but when the size of the subsystem increases for n equals 4, observe that it's possible to use classical shadows and achieve better results with very few measurements compared with direct measurements. Okay, and finally we had chosen a state at random, and we obtain, okay, for any equal 3 is not clear, it oscillates a lot, but for a subsystem of size 4, it's possible to see that using classical shadows, we are very close to the exact value, while using the direct measurements, you need almost 100 measurements more compared with classical shadows. Okay, this is a simple application. This result, they're not published yet, but we'll hope to publish it soon. Now I will talk an application of classical shadows that will be very clear in a situation in which classical shadows is very useful. Okay, for that I use Falcon algorithm. Falcon means feedback-based quantum optimization algorithm. This article was published 2 years ago. What's the idea of this algorithm? Okay, suppose that you have the Schrödinger equation with the following Hamiltonian. HP here is the Hamiltonian of the problem in which you encode your problem. HD is the driver Hamiltonian, quite similar with variational algorithms that you already know. But now we have a control parameter, beta. It depends on time. What's the goal? The goal here is to find this parameter that minimizes the energy of the system after certain time of evolution, okay? And solve this problem, the authors use an inspiration on the Lyapunov control theory, okay? For that, it's necessary to choose a cost function. Here, it's called J, and this cost function is the expected value of the Hamiltonian problem, okay? So, basic idea, as in general for variational algorithms, you want to achieve the ground state of your Hamiltonian that describe the problem of the system, okay? And how to minimize that? The idea is to find a connection between the cost function and your control parameter. To do that, you take the time derivative of this expression, and then you find a connection between J and beta, and this parameter depends on the commutator between the driver Hamiltonian and the problem Hamiltonian. As you don't know your parameter beta, you can choose as minus A of t, and you do this because in this way we'll be sure that the parameter J will decrease monotonically over time. For that reason, until you find the ground state of the system, okay? But it's important to observe that when you choose beta as function of this term, observe that you don't know psi of t, that's the solution of the problem. So it's a recursive problem, okay? Okay, the idea is, as time goes on, we will achieving the ground state of the system. And to implement the evolution of the state psi, we use the Trotter-Suzuki expansion. As much of you already know, that widely used in variational algorithms. Okay, this is one operator that depends only on the problem Hamiltonian, and the driver Hamiltonian, it's multiplied by beta, the parameter that we don't know, okay? Observe that they appear alternately, okay? So the first step is, okay, beta is 0 at the beginning, then we evolve with this initial value beta, and we obtain a new state. With this new state, we obtain this expected value. And as you can notice here, this expected value will be the place where we use classical shadow. Okay, that's the idea. Okay, sorry. Okay, this is the first step, and we'll use this new value of beta, replacing in a second layer, and so on until you have many layers. And finally, after many layers, and your beta value is in your desired value, using a convergence criteria, you perform measurements in the z-basis, because the Hamiltonian problem is diagonal in the z-basis, as people do by using Ising Hamiltonian. Then we'll find the ground state of the system. Okay? That's the idea. So, okay, to use classical shadows in Falcon, so it's necessary to replace these measurement stages by classical shadows. Okay? And as an application, we solve the max cut problem. Okay? The idea of max cut problem is to identify, okay, a graph partition, as you can see, this dashed line, that maximize the number of edges cut. Okay? Here is a solution for this particular graph. Okay? There is a partition. And to implement that in a quantum computer, the Hamiltonian problem is this one. The driver Hamiltonian is this one. And notice that the term that depends on the commutator now depends only on the tensor product of two observables. Okay? Remember that that term, the W, is related, and W now is 2. Okay? So it's necessary to evaluate the expected values of these operators here. So the strategy that we use here is randomized using classical shadows by draw from this group, as I mentioned before. But if you pay attention, you can see that the X operator is not here. So it's not necessary to perform measurements along the Y direction. So you just perform measurement along the Y and Z direction. Okay? For instance, if your problem has 4 vertices, the number of operators in beta is 8. So it's necessary to evaluate 8 expected values of these operators, and the cost function has just 4 operators. And for n equal 10 vertices, then beta will have 34 expected values, and the cost function 17 expected values. This shows a condition in which classical shadows becomes useful. Okay? And this is our first result. The time step of the evolution is .1. The number of measurements in classical shadows is this one, and direct measurements is the same. The exact value in which you can evaluate exactly, okay, analytically maybe, you obtain this continuous black line and use classical shadows, the red line, and direct measurements, the blue line. It's important to observe that with direct measurements and classical shadows, you can see random oscillations around the mean value of beta. And in the horizontal axis, you can find the total number of layers, and here is beta. The idea of beta is that at the end of the computation, the value of beta we expect to be 0 because you have at the final Hamiltonian just the problem Hamiltonian. Okay? Okay. Now, if you calculate the costing function, we obtain this behavior. Okay, this is the total number of measurements in the system. This is an example. As the number of layers increases, you can find the solutions to our max cut problem. This means 0, 1, 2, 3, and so on. They are written in the base 2. So, for instance, 5 is 0, 1. This is for any equal 4, so 0, 1, 0, 1. Okay, this is one solution, and the other solution is 1, 0, 1, 0. Okay. If you increase the number of vertices to 6 now, observe that to achieve 99% of the exact value of beta using classical shadows or direct measurements, using classical shadows, you need just around 32,000 measurements, while use direct measurements, use much more, okay? If your problem, okay, this is the value for the constant function, okay? If you increase for 80 vertices, observe that the number of measurements using classical shadows is basically the same, while the number of measurements using direct measurements is much, much greater. This is the cost function. And finally, it's possible to see a very huge difference. So using classical shadows, it seems that it is very interesting for this problem. Okay. Now, the last part of my talk, I will show you how to use Walsh functions as an answers to variational quantum algorithms. And the example you have used is how to use these ansatz algorithm, this ansatz circuit to obtain, to do a regression in a set of data, in a data set. Okay? What is this? Okay, what are Walsh functions? Walsh functions, you can think in the same line when you think about Fourier expansion. Okay? Instead of sine, cosine, and so on, we have now these functions. Okay? And these functions will be used to write a general function. This is the base. Okay? This is a simulation of the sinc function, just using 10, at most 10 qubits. It's possible using this base function to fit the sinc function, okay? The black line is the exact result, and the approximate result obtained through the Walsh function. We obtain this description, this fit, okay? Okay, the number of qubits, as you can see, is very small. Just with 10 qubits, it's possible to fit very well the sinc function. However, the depth of the circuit, the quantum circuit, is not so friendly, okay? Because it increases exponentially with the number of qubits, okay? And okay, in the previous slides, I showed the classical representation of Walsh functions, and now this is the way how you represent using quantum mechanics. The idea that the Walsh weights, they will be represented using the tensor product of the operators, okay? and the action of these operators on the basis states. These are the basis states in the computational basis. We obtain the classical Walsh functions. That's the idea. So if you have a F operator instead of a F function, you describe this operator as a linear combination of operator of the Walsh basis. Okay? And this function, you suppose that it's a Hermitian operator, so that the evolution operator is the exponential of this Hermitian operator. Okay? The nice part is that this kind of operator, that exponential of the tensor product of Z operators, can be very well described using C0 gates and rotation around the Z-axis. As I mentioned before, the depth of the circuit, it doesn't scale much well, but it increases with the system size. So this circuit to prepare a given state is basically you enter all the qubits in the zero state. Then we apply Hadamard gate, so we create a equally superposed state among all the base states. Then we apply that unitary operation that is written using Walsh operators. And then it's necessary to use an auxiliary qubit to have access to the evolution of the F function. It's necessary to observe that we are considering a epsilon zero parameter that it is very small. So it's possible to expand this exponential term and take the first order in this expansion, and this first order will be exactly the action. The action of the. It's okay. Okay. No. Hello. It's okay. Okay. The action of the F operator on the basis states. Okay. So at the end, we will get the F state or the F function represented in a quantum circuit. It is not working. Hello? Okay, thank you, Marco. Okay, so this is our final quantum circuit. And what is the idea now? Okay, this was a proposal to use quantum Walsh operators to obtain or to prepare quantum states. Our idea here is, okay, let's take this kind of circuit as an ansatz to use it in quantum machine learning to fit, a data set, okay? That's the idea. So we define the cost function in this way. The cost function is the infidelity, 1 minus the fidelity between the target state and the approximate one. Using classical methods, it's possible to achieve the minimum value of this cost function. And now we are using this as a protocol to in quantum machine learning. Okay. Here, okay, the animation isn't working. Sorry. This is what we have implemented first. Okay, to recover the sync function. This is the number of epochs you can find here. Okay, 1 minus the fidelity was established as less than 10 to minus 4. And this is when we introduce noise in our sync function. And our question was, okay, can I use this kind of ansatz circuit to obtain a good fit when you have noise data, okay? And it seems that it works well, although for who are specialists on machine learning, you observe that, okay, this is similar to overfitting, right? But the question is, okay, it seems that these variational ansatz based on quantum Walsh operators, it seems that is very useful and to fit smooth functions or random functions, okay? As you can see here, this is the Bitcoin price using our method. You can see our estimate is it describes well, but it's not clear. That's why I present all these results. All these results, as I mentioned at the beginning of my talk, they are fresh results. So I am totally open to discuss. Okay, they are not defined yet. Maybe you can find some problems or can have new ideas about these problems, and you can try to find solutions for them. Okay. We reproduce this time series using just 7 qubits. The problem that is the depth of the circuit depends on 2 to the power of 7. Okay, so for nowadays, maybe not too much. Okay, but it's nice. Okay, it's a Bitcoin time series. Okay, during 4 months. Okay, and finally, I'd like to invite all of you to participate in the 7º workshop de computação quântica that will be held in city of Florianópolis in the south of Brazil. There you can find a lot of interesting things. There are talks, mini course, quantum hackathon, quantum podcast. It's also lightning talks, exposition, presentation of posters. This totally for free, okay? And you can attend our workshop in person or online, okay? And if you want to subscribe, just use your smartphone, okay? And okay, just to finish, what are the challenges and the future perspectives? Okay, first proposal is to adapt a CAT quantum programming quantum platform. Hello? 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 Can you hear me? It's okay. Now our next steps are, okay, to adapt CAT quantum platform to hardware, to quantum hardware. That's what we're doing now. Not me exactly, but Evandro Chagas Ribeiro and a few students. And in the case of classical shadows, you are using new versions of classical shadows. They're randomized. They are more clever implementations of classical shadows. And in the literature, it's possible to find very good results, mainly if you are interested in problems of quantum chemistry. That's very good for quantum chemistry. You can also apply these results of classical shadows in other problems, such as in fundamental problems of quantum information. For instance, quantum contextuality, quantum steering, because in those measures, they depend on a huge number of observables. Okay, so it's sound nice. And the next step, try to find a quantum ansatz circuit based on Walsh coefficients, but with a depth that doesn't scale with exponentially number of cubes, okay? These are our next steps. And if you try to talk to me or our research group, you can find me on all these links, okay? Thank you.
Okay. Thank you very much, Eduardo, for this very nice talk. So we are now open for questions. Question.
Obrigado pela palestra, Eduardo. Eu tenho uma pergunta e uma sugestão. Não, né? Bom, voltou a funcionar. E a minha pergunta é naquela preparação de estados usando o WASH. Né? O bit auxiliar tem uma pós-medição, né, que ele só funciona se der 0 ou 1. Tem alguma garantia que aquela probabilidade vai ser alta ou pode acontecer algum caso que a probabilidade vai ser muito pequena e você nunca consegue preparar o estado? Tá? Essa é uma pergunta. E aí, só para concluir, eu acho que parou de funcionar agora, mas tem também uma... Eu tenho também uma sugestão, que é mais da parte variacional agora, que você perguntou, será que dá para reduzir a profundidade do circuito? E eu vi alguns artigos que eles fazem o seguinte, olha, é variacional, mas eu vou fazer em vários componentes separados, e aí vai ter um custo exponencial no tamanho dos componentes, mas normalmente isso dá uma boa aproximação, né? Porque você não sabe encontrar os coeficientes de componentes separados que aproximem a função como um todo, mas o circuito quântico variacional acaba aproximando, mas você perde um pouco ali do emaranhamento.
Okay? Okay, the question was okay?
A questão era mais sobre o bit auxiliar. Se pode ser uma probabilidade tão pequena que você nunca consegue, na prática, construir o estado.
Okay. In general, we are able to measure this auxiliary qubit, okay? Actually, it depends on the gates you use, the Hadamard gates that it's have balanced, so there is no problem. We always find a probability that's no null. Okay, so there is no problem in this question. Related to the quantum variational circuit, I agree with your idea. We are already working on this, and we are thinking that, okay, the original quantum circuit was totally inspired using quantum Walsh series, but the idea, okay, if you remove some parts of your quantum circuit, maybe you can find new parameters that are able to compensate this kind. But we are not sure. This is the next step. But you can talk after about your proposal. It seems very nice. And we are totally open to talk and collaborate. Thank you, Adenilton.
So thank you very much. I think we are very much advanced in time. So I think that anyone can use the coffee break to ask Professor Eduardo. But let's thank the speaker again. And we have just an announcement.
Olá. Vamos então só reforçar alguns avisos e o sorteio do livro que a gente faz sempre ao final de cada plenária.